So my main research area is focusing on bioenergy and resource recovery from waste and wastewater, biosensing for monitoring environmental pollutants and bioremediation. Some of the topics that we are working these days are obviously anaerobic digestion, fermentation, microbial electrochemical technologies. We are also working on a lot of different physicochemical processes as well. But one of the exciting things that we are doing right now is how to actually convert some of the greenhouse gases to some value-added products. That's kind of like the one of the interesting topic that we are working on right now.
Between the anaerobic digestion and microbial electrochemical cells, because those are, I think, the major two topics that you worked during your master PhD, and now you are continuing your research was more advancing those. Which one of those two is more interesting or appealing to you? A little bit tricky.
That's really a tricky question. It's kind of like you have two kids and now you have to decide on one. I think, I love both topics. For anaerobic digestion, we do a lot of things with industries, and we are fortunate that some of the topics that we worked on, we are actually could move them from or transition them from lab to pilot or from bench to pilot scale. That we are exploring right now. So that's kind of exciting thing to see that, you can scale up or validate some of the ideas that you did in the bench. For microbial electrochemical technologies, that's, I think, that's a very exciting area. You can learn a lot of new fundamentals. So there are still a lot of new fundamentals there. And to scale up microbial electrochemical technologies, it's quite challenging still. Maybe some of the ideas like biosensing we can actually apply to the field in near future. But obviously, like when you want to build or design some large system for a treatment, and that's still quite challenging. But still, it's, I think, a very exciting field for me. I remember, when I was grad student, when you first time you see some positive current, on the computer screen from some reactor, that's actually very rewarding or refreshing thing to see.
Yeah.
I'm not sure whether my students can feel the same or not, but both topics are really, I really enjoy both topics. Yeah.
But I feel that you enjoy more the MAC.
Well, I enjoy both, honestly speaking. And I think, one of the things, I worked on anaerobic digestion during my master's.
Yep.
And during my PhD, I worked mostly on microbial electrochemical technologies. But when I started my independent career, I could connect both of them. Yes. Actually, there are a lot of overlaps in not just in fundamentals, also in application. So for example, we are trying to see how we can integrate microbial electrochemical technologies to upgrade biogas that is coming out from digester and convert that into renewable natural gas or convert that into high value-added product. Right? So there are a lot of actually complementary things between two topics.
That's a quite interesting topic that is converting either the methane or carbon dioxide, the biogas that produced from the anaerobic digestion into RNG or value-added product, whatever. Can you tell us elaborate a little bit on that topic? So how are you using that MEC to upgrade the biogas?
Yes, and that's actually a good question. So one of the nowadays, there is a lot of interest on, how we can actually upgrade the biogas to renewable natural gas and inject to the grid, because we know that we can, kind of combust biogas in combined heat and power generation unit and produce heat and electricity. But most of the actually facilities, they are forced to actually flare the biogas, right? Because sometimes upgrading is quite challenging. So we are developing microbial electrosynthesis cells to actually convert those. So biogas, we have carbon dioxide, methane, and a lot of other impurities like hydrogen sulfide. So we are actually using microbial electrosynthesis cell to actually using some electroactive microbes to actually convert that carbon dioxide to additional methane. So that means you get about end of the process, you can get about 95 to 99% methane. So it's kind of almost like natural gas that you can inject to the grid. And one of the interesting thing we recently actually found that we could possibly use that technique for both converting carbon dioxide to methane and also remove the sulfide from biogas. So that's kind of can give you dual benefit. So it can possibly act as a standalone system for both processes.
What are the challenges for that kind of line?
Yes, challenges is one of the major challenges is how to scale up this idea, right? How you push it from bench to pilot or in the field. And one of the major challenges mass transfer limitation. So because solubility of those gas is not very good, right? Very low. So we are trying to explore some innovative methods how actually we can enhance the mass transfer limitation and kind of make the process more faster. So we are actually currently working on a couple of different ideas, and hopefully we'll have some exciting things very soon. Yeah.
Hopefully, yeah. So we always hear about that, and you mentioned to it combining the anaerobic digestion with MAC to upgrade it, not just to upgrade the biogas, but to enhance the process itself.
Yeah.
How do you see that as combining the anaerobic digestion process with the MAC as feasible technology to be happen, and what are the challenges?
Yes, we can also actually directly apply the microbial electrochemical technology or directly integrate like in a in a modular system. So where actually anaerobic digestion and both microbial electrolysis cell can actually occur together. So that process can actually offer us to overcome some of the kinetic limitation in the process, okay? But at the same time, it's quite challenging because, we can, sometimes we feel that, okay, we can just insert some electrode in the bioreactor and apply some voltage and it's gonna start working, right? So, but still, in existing facilities, to retrofit this kind of idea is quite challenging, right?
Yep.
Because it's quite challenging. So when something is promising, at the same time, it comes with a lot of challenges as well. And that's our job to actually kind of, overcome those challenges. I think we are on the right track. Yes, it's going to take some time to scale up this kind of idea, because I think if I show some bench scale results and ask industry, okay, that actually works perfectly well in my lab, and let us insert some electrode in the digester, I think they are not going to accept that.
Exactly.
We have to go for some pilot validation and all. We still have to do a lot of things to actually convince industries to actually adopt this kind of ideas and how to engineer the idea, right? So possibly system not going to look like same as what we have in the lab, right? So we still have to do a lot of things. But one of the thing I kind of experience that sometimes students feel that, okay, there is not a lot of application of microbial electrochemical technologies in the field. So maybe if I do my master's or PhD in this topic, maybe it's
Not gonna
going to
find a
be
job.
quite challenging for me to find a job. Actually, that's I think it's not correct. Okay, if you are working on a topic for your master's or PhD, that not necessarily mean that you're going to be doing that same thing for rest of your life. In grad school, I think most important thing we get a training. That's a training.
Yes.
Actually, we learn how to actually think outside the box. We learn how to critically analyze something, right? And that give you a different perspective to see things differently, right? So